So morning all, we're going to be moving on to atomic physics this morning. So here we're going to look at how we were able to discover by direct measurement or by indirect proof what the atom looks like. All right, now the atom is, you know, the building block of everything around us. Everything around us is made up of atoms. Okay, so we needed to know, right? We had an idea long ago that yes, things were made up of very small particles that we cannot see. Hold on. All right, so um, this is how some very brilliant people came up with methods to determine, either by accident or directly, to determine what the atom is made up of. Just as chemistry students, what are the three main components of the atom? Anybody can tell me?
Which are the protons, the neutrons, and electrons.
Protons, neutrons, and electrons. Where in the atom do the protons and neutrons lie?
In the nucleus.
In the nucleus. Very good. Right? So that is what we know the atom to look like. You all know that we have shells and stuff to put where the electrons are, right? You all should have done shells where you have 2 electrons in your first shell, um, 8 bonding electrons in the second shell. Have you all done that?
Yes, miss.
Good.
Yes, miss.
Right? So how did we discover, right? How on earth can we know that all the protons lie in the nucleus? And how do we know that the electrons arrange themselves in shells, right? It's not like, 150 years ago where people were still, the telephone wasn't invented, much less the internet, right? We hadn't gone out into space as yet. Cars had not been invented as yet. The engine, the diesel and gasoline engine had not been discovered as yet. So how on earth could they determine these things? Right? It took some pretty brilliant people, either intentionally or by accident. You all are going to see we have a lot of wonderful accidents, right? That happen. Not really accidents as in a whoops and a mistake, more like they were looking for something and they discovered something else in the meantime. Now, this is the beautiful thing about science, right? When you have an open mind, you don't just say, if you're doing an experiment, right, a very expensive experiment that is, and your results don't come out properly, the first thing people will say, well, you know what, the apparatus wrong, we need to throw it away, not working. We're not looking at that. We have to learn to look and see why is something behaving the way it behaves. That is the hallmark between a true scientific inquiry with an inquisitive mind versus those who just dare to learn, right, and not think. So this is the beautiful thing here. We had some really brilliant guys, very little bit of girls back then, but that's all right. It changed now, right? Where they saw something in front of them and they realized that, there's a reason why these things happen, and they investigated it and they changed the world in the terms of science. So it's a wonderful topic. I love this topic of the evolution of the atomic model. So let's go through it and see. So if I sound a little too excited, it's probably because I really, really, really think this was awesome of our wonderful human race, even though nowadays we see in the bad parts of human race, but whatever. So the atomic model, all right, the current, reading from the screen, the current atomic model consists of negatively charged electrons, sorry, circling a dense nucleus. In this nucleus, particles such as protons, neutrons, and other subatomic particles can be found. We're not going to go through the other subatomic particles, but if you want to read up on it, by all means, go ahead. We have things like neutrinos, we have quarks, we have muons, pions, a whole long list of things that lie within the nucleus. The nucleus is like a little universe by itself. But at our level, the only thing we are concerned with are electrons, protons, and neutrons. And you all do know where they lie because you all are chemistry students. So continue reading. When the atom was first being investigated, the main components of the atoms, which are the electrons, protons, and neutrons, had not yet been discovered. So let's think about it. We are trying to understand how an atom works, what causes an atom to work, what makes up an atom, and we had no idea what it was comprised of. Let's think about if you all get a piece of cake, right? Eat a piece of cake, right? Regular sponge or chocolate cake. Will you know that there is egg in that cake? Think about it.
Let's see what we can answer that question.
Yeah, I want an answer to that question. This is leading to your thinking, right? If you ate
No,
a piece
miss.
of cake, you would not know that it had egg in it, and egg is a very important part of cake, right? If you all had encountered a very good baker and they had made vegetarian cake, which is cake without eggs, and regular cake, which is cake with eggs, if it's a really good baker, there's no way for you to know the difference. So here we're trying to discover if somebody had used um, all-purpose flour and somebody had used baking flour, there's no way you can know. So you have to think, all right, this is what the scientists were faced with. They were trying to discover what made up an atom, right, without knowing what was inside of that atom. It's a big task, but here is where we have to make a guess. Usually it's a hypothesis. What's a hypothesis? It's a statement where we put forward an idea and now we test it. So this was the first idea that came out. Yes, it looks funny, but you have to start somewhere. So the very first model was what we call the plum pudding model. In the mid 1800s, we're talking like 1850s, mid 1800s, the newest idea for the atom was that it consisted of a ball of positive charge with random negative charges in it. Now, why positive and negative? They knew at that time that there were positive and negative charges because they had now started exploring electricity. Imagine they exploring electricity and they did not know about the electron as yet. All right, kind of weird, but it worked out to the end of the day, obviously. All right, they knew that we have positive charges and they knew that we have negative charges. And using science and math, they were able to determine, a positive and a negative will give you 0. That looks like a face. Oh, well. All right, we know a positive and a negative will give you 0. Positive 1 and negative 1 added together will give you 0. They knew that everything around us had a neutral charge. All right, what does neutral charge mean? This means that the overall charge was 0. They weren't excess positive and they weren't excess negative. So in their minds, they knew that atoms, which are the building blocks of everything solid around us, had to have equal amounts of positive and negative charge. You all following so far, right?
Yes, miss.
Good. So this is what they came up with. They came up with an idea. You know what? Okay. All right. So this is the idea they came up with. They said probably atoms are a ball of positive charges with enough electrons or enough negative charges in it to neutralize it. Now, we as science students and science enthusiasts, we know that this is not what happened, but that you have to go back. This is 1800s. They are now trying to figure out what it looked like. So let's put out some sort of idea. And when we have an idea, we can now test to see whether our idea was true or not. So let's continue reading. These negative and positive charges balanced out in each other in order to maintain a neutral charge. The model looked like the old English, like an old English dessert called the plum pudding. Right? If you all actually want to know, plum pudding is very, very close to what our black cake is without, the browning in it. All right, so there's an old British dessert, English dessert called plum pudding. All right, and it basically looked like this, where the brown part was the pudding, that's your positive section. So let's imagine as the positive charge, and all the little cherries and fruits and whatnot in it were the negative charges. So whoever had put this out, imagine this is what they put out in the scientific um, paper. Right, that would have been J.J. Thomson would have put this out in a scientific paper. And then somebody said, just jokingly, that looking like a pudding we had last week when, we went by our grandmother or whatever. And it's stuck, right? All kind of weird little names stick very easily. We all know we never remember the proper name for something. But if I give you a nickname or I give you a funny name, we tend to remember that better. So very jokingly and very quickly, this became the plum pudding model where, sorry. Okay, all right, where the model that it put out was a positive ball of charge. Well, of course, these are very, very, very small balls of charge, right? And these balls of charge had negative charges in them to neutralize your overall charge. So this was the accepted model at the time because somebody had to throw an idea out there rather than saying, you know what, we don't know. They still really didn't know, but at least they had this starting point from somewhere. All right, so this was the accepted model until the 1880s, 1890s. They said, you know what, we have no way of testing and showing it, but at least we have an idea. This is what it looks like. So let's take it for the while. Now comes the experiment that changed the world in physics, right? Or the accident that changed everything. Yeah, I sound excited because it's really, really cool. The more you learn about this experiment, the more awesome it was in its what you call the word, in its meaning and interpretations. So we have the discovery of the nucleus. We are now going to move from the plum pudding model to something that looks more familiar. So this is called the Geiger-Marsden experiment. Everybody here that we've talked about have won Nobel Prizes. Here was, at the top was J.J. Thomson. Right? J.J. Thomson was the university lecturer who oversaw Geiger and Marsden when they were doing their research. So they were all linked together. Right? And if you want to go, this is the mecca, the absolute capital of atomic physics back then was the University of Manchester. Right? University of Manchester is where they did all of these experiments to the point where the building they were doing these experiments at is so radioactive right now because they didn't know about radioactivity then. They've locked it off and nobody can go in the building again. But I'll come to that story a little later. So the Geiger-Marsden experiment. We have to jump a little bit. In this experiment, alpha particles, now an alpha particle is a positively charged radioactive emission. So it's basically, what is helium? Do you know where helium lies in the periodic table? Yeah?
The second one.
The second one. How many electrons are in a helium atom?
I don't know for sure, man.
You said the word 2, right? Right? It has 2 electrons. So if it has a neutral charge, it will also have 2 protons. And the nice thing about helium, it also has 2 neutrons. So that means, let's just go here, a helium nucleus will have 2 protons, 2 neutrons, and 2 electrons spinning around it. An alpha particle is a particle that looks like the nucleus of a helium atom. So what it is, it's basically 2 protons and 2 neutrons that flies around in a very, very high speed that they use, right? Well, that comes out during radioactive events and reactions and whatnot. So they had discovered radioactive material at the same time. So this is when they were all playing with a lot of things. All right, of course, they didn't know that radioactivity was bad as yet. They really didn't know it was bad as yet. So they were enjoying finding out, you know, we have this new cool little particle, right, that can pass through things, that has a lot of energy. But we know differently now. We know that radioactive particles and radioactive emissions are very dangerous. They didn't know as yet. Right? So they had this alpha particle, which is basically a little positive charge that has 2 protons and 2 neutrons. So it has a positive, a +2 charge. Let's remember it has a +2 charge. All right, this is what I want you all to remember at the top of your head. All right, your alpha particle has a +2 charge. Just to go back through, pulling all our physics knowledge so far, will a positive charge be attracted or repelled by another positive charge?
Repel.
We repel. So we putting that in the back, well, not the back, in the front of our mind right now, because that's going to help explain a lot of things here. All right, so alpha particle has a +2 charge. So in this experiment, alpha particles, which are positively charged radioactive emissions, were fired into a very thin gold foil. Very, very thin. When I tell you thin, it was so thin that that foil was probably about 5 or 6 atoms thick. If you breathe on it too, if you breathe on it too hard, it will actually fall apart. We have some really, really thin gold foil in school too, and it's so fragile with the moisture in our atmosphere. As soon as we touch it, it falls apart. So, right, so this is very, very thin gold foil. What they would do, they were firing alpha particles in it. Why they were doing this? They were trying to investigate how alpha particles get affected by different materials. So they were doing a very completely different experiment. They were here investigating how alpha particles behave, because alpha particles were just discovered, and everyone who had the equipment and universities that had equipment, they were jumping on, let's see what these things are made of. All right, so they were not even looking to break open and to change the world of physics. They were just trying to see, okay, we have this new particle, let's see what it does. So let's see again what they do. In this experiment, they fired the alpha particles into a very thin gold foil, and their passage was noted. Most of the particles went through the foil, but very few, meaning less than 1 in 10,000, 10,000, y'all, look at that number, 1 in 10,000, would get deflected. All right, so all of them. So imagine, we have the diagram coming up below. So as the gold foil, right, and all of the alpha particles will fire through. Now these move really fast, nearly to the speed of light. If you want to know what the speed of light is 300,000 kilometers a second. So light will travel 300,000 kilometers in 1 second. That's how fast light is. All right, so these alpha particles travel nearly at that speed. So they were all traveling through fine, because the experiment was here to see how metals and the alpha particles interact. So they were expecting to see this just fly through normal, right? 10,000 of them. And ever so often this will happen. One of them will get deflected, right? One of them will get deflected and go somewhere else. And even rarer than that, some of them will come hit the foil and bounce back. So according to the current model, then this should not happen. right? So they were really, really, really confused. Let's go down to the diagram of what the actual apparatus look like. So we have here, they use radium. The radium is contained into a lead container because lead containers protect or stop radioactivity from flowing out of it. So they had a little container of lead. All right, there was radium and there was a little tiny little hole in the middle here, a little tiny, line here that can shoot out the alpha particles. And these alpha particles will hit the very, very, very thin gold foil. Right, and all of them flow through and hit what we had here is a little photographic film. So every time these particles hit the screen, you would see a little flash of light, right? Little flash of light, little flash of light, right? So you see a little teeny tiny flashlight. So you can see when it passes through. So even though these things are very small and they're invisible to the human eye, they can still see where it hit. You'll ever close your eyes, or yeah, if you close your eyes, you ever see a little small little flash of light ever so often, a little pinprick of light in your eyes?
Yeah, miss.
All right, anybody here ever noticed that?
Yeah, miss.
Yeah, ma'am.
Let me blow your minds right now. Sometimes that little tiny flash of light is a neutrino passing through your body. A neutrino is a little particle that comes out of the atom that can only be produced by exploding stars. How amazing is that? Ever so often, they can pass through the human body, they pass through the earth like nothing, they don't affect anybody, they don't care about anybody. Right? But ever so often, if that neutrino hits the right cell in your eye, it causes a little flash. And we see that little flash. Pretty cool, huh? I find that's amazing. Now we can see these little tiny
Mas I
things.
used to think I going mad.
What?
I used to think I going mad.
No. All right. Now that can happen. And if you rub your eye too much, what's going to happen? You end up causing some of these cells to go a little crazy in your eye. When we do the human eye, when we go into the physics of the eye, we will see why you see the things you see in your eye. But ever so often, you can just be doing something. You see a little tiny flash in your eye. It doesn't happen very often. That's a couple times a year. That is actually a neutrino that came out from a star that exploded many millions of years ago, passing through your eye, hitting the right cell and causing a little flash. That's beyond amazing and beyond cool that we could experience these little things. So the same thing happened here. Anytime these alpha particles hit this little photographic film, it'll cause a little flash of light. So as they were doing it, so here, they were really counting all the flashes. They were counting it. Back then, you had nothing else to do but count 10,000 flashes of light, right? But ever so often, one will get deflected. Ever so often, one will get deflected. And even worse, they will rebound and come and fly back. So what they were expecting, because the model that they had back then was the plum pudding model. And the plum pudding model said that we had a neutral atom. And if we had a neutral atom, that means that, this is a little ball of positive charge. So the whole thing overall had no charge. So that means that my little, let's get a nice radioactivity color. All right, so if I took my little alpha particle, that alpha particle will just come and fly through. Seriously, behave. Right? That little alpha particle will just fly through the atoms with no deviation. Why? Because this has an overall zero charge. And with it having no charge, right, it's not going to be affected. So this happening, you see this happening here? I think that Geiger and Marsden seriously thought that they were going crazy. If you want to know how weird this was happening, imagine if we had a napkin, a bounty paper, not even a bounty because that's expensive, a soft and pretty napkin, and we took a gun and fired a bullet into this napkin. Imagine that bullet bouncing off that napkin. Wouldn't you think you're going mad? I would think I was going crazy. right? Because if you, this is how this was supposed to work. It's the same as saying you were taking a gun and firing a bullet into a napkin, a paper towel, right? And obviously, well, yeah, you say, Missy, what stupidness you talking? Of course, a bullet going to fly through a paper towel like nothing, right? Imagine that bullet getting either deflected or even worse yet, that bullet getting bouncing off the napkin and going to the next direction. This is how mind blowing this experiment was. Now, it doesn't happen very often, one in every 10,000 or less. But the fact that it happened, it meant something. So rather than thinking that they were going crazy, they sat down and they thought. And it's like, you know what? We are looking at something different here, right? What we are looking at means something. And their interaction, I don't have a good one of this, right? What they came up with was that, you know, how we think, what we think about the atom is probably wrong. So let's see how what they came up with, right? How that changed the entire game, right? What they came up with, rather than thinking, yes, we're going crazy, they thought, and they thought and they really thought about it. And of course, they brought in their lecturer who was overseeing them and whatnot. It's like, you know, we're seeing this happening. And then, of course, their lecturer would have come in and run the experiment too and realize, okay, these two guys not going crazy in my lab, right? Well, they weren't going crazy as yet. So they thought about it and they said, you know, the atoms that are supposed to fly through normally, if I had had my atoms flying through the regular model, they would fly through normal, you know, with no deviation whatsoever, because all our atoms are nice and neutral. Yes? Question? Yes, Mark?
Mr. said how they weren't going crazy as yet. What that means?
They weren't going crazy as yet because, as I said, the building, the University of Manchester, where they did all of the experiments, they were using a lot of radioactive material, right? They used them day in, day out without protective shielding. All they did was just use a little forceps to pick it up and put it down on the table. I saw somebody pick it up with their hand already. With this level of exposure to the radioactive material, many things can happen to you. You can develop cancers, right? Some of those cancers can affect your brain, right? They didn't know about all these things. Just anybody here now jumping the gun? Anybody here ever heard of Madame Curie?
No.
You all are going to have to learn about Madame Curie. Madame Curie was the first woman to win a Nobel Prize in any field, right? And she won it. She's the only person to win a Nobel Prize in 2 different areas. Only person up to now, right? She won a Nobel Prize in chemistry and she won a Nobel Prize in physics, right? Madame Curie is the one who discovered the dangers of radioactivity. And her notebooks, because she was using it so much and whatnot, and you know, of course, you use your hand, you touch it, you're close to the radioactive materials. Her notebooks are too radioactive to look at for the next 300 years. So you can't go and physically touch her notebook without being exposed to radioactive emissions. So for the next 300 years, nobody could touch those books. Then it'll be at a safe level. So back then, because they used so much radioactive material and they didn't know it was dangerous, right? Yes, you could have gotten cancers. You would have started seeing um, immune problems. They would have started getting ill, right? Some people, some of those cancers start depleting brain cells. So you know, look like people being crazy. Back then, a lot of illnesses were either thought to be mental. You wouldn't believe how many illnesses were thought to be mental illnesses. Ladies, PMS they thought was a mental illness. PMS that I know people to go and get blood transfusions for, right? And who have to get morphine for and require surgery to fix themselves. They thought that was mental illness. They thought labor was actually being over exaggerated. right? They thought that headaches were usually not a physical ailment. This is what they thought back then. So coming back to the original topic. All right, so they weren't going crazy. They don't think they were going crazy as yet. Lots of scientists do go a little crazy sometimes. We think too much. All right, so back to the original story at hand. These particles are supposed to fly through this atom like nobody business, not getting deflected at all. Now, going back, remember we said that the alpha particles have a +2 charge. And this is where they thought, an alpha particle has a +2 charge. And I know if I take that alpha particle and bring it near to another positive charge, what's going to happen? One of two things are going to happen. It's either going to, if I take my alpha particle, right, and I take my alpha particle and I bring it close to that positive charge, right? So if it's going close to the positive charge, it's going to want to move away from that positive charge, or even worse yet, why is it doing that? Or even worse yet, it can go hit the positive charge and bounce off. So this is where they actually sat down and thought, you know what? It has to be the positive charges interacting with each other. All right, this is where everybody sit down and they talk. And I'm sure some guys like, yo, I wonder if it's charges interacting with each other. And then somebody else thought and they realized, yeah, you're probably right. So all of the alpha particles that fly through nice and easy, that was fine. But anytime an alpha particle came really close to the nucleus, it would get deflected. And if it happened to come head on to the nucleus, it will get completely rebounded, meaning it bounces back to where it came from. So this is where they realize, you know what? We don't have it right. This ball of positive charge with random negative charges is not what it looks like. We are coming up with that somewhere in the atom, there is a small area of positive charges concentrated, right? And then the electrons have to be really far away for us to be able to measure or be experienced or to experience this positive charge in the middle. So what are the implications of the Geiger-Mason experiment, or we call this the gold foil experiment? Let's see what is the implications of the gold foil experiment. One, so the implication of this experiment, one, there is a central positively charged core of an atom, and we all know that to be the nucleus. All right, so this is where they discovered the nucleus. They changed the world with one experiment. So they discovered, obviously, the atom, rather than looking like this, our plum pudding, which is our positive ball with random negative charges. No, we are now going to see that we have a ball of positive charge in the middle of our atom. And then the distance between the core or the nucleus and the electron is very large. Why are they saying it's very large? Because even if here, say this is the next nucleus of your next atom, and this is where your electrons are. Remember, 10,000 alpha particles flew through this without getting deflected. 10,000, more than 10,000. So that meant the possibility and the probability of hitting that nucleus was very small. And the only way that could happen is because the distance between one nucleus to another was relatively pretty large. All right, so the distance between the nucleus and your electron is very large, and that matter is mostly made up of empty space. We have this little, I think one of our physics textbooks has it. You all know the Atabolan, is the Atabolan or here's the Crawford Stadium, right? Anybody ever been to the Hasely Crawford Stadium, or at least knows what it looks like, how big it is? Yeah?
Yes, miss.
Right. Imagine we take a pigeon peas and put it inside the middle of the field of the Hasely Crawford Stadium. You all can imagine the size of a pigeon peas, right? A pigeon peas that's in season right now. Imagine this pigeon peas is the size of a nucleus, and the top stand of the Hazley Crawford Stadium is where your first electron will be. That is how big the atom is if you were to compare the distances. Right? If your nucleus would be the size of a pigeon peas, a single pigeon peas. Right? And the nearest electron, essentially, if you were to blow it up to our standards, will be the top row of the Hazley Crawford Stadium. So what that means, you see all of this space inside here is nothing. Oops, sorry, how did that happen? All of this is empty space. 99.9% of an atom is empty space. All right, now the implications for that too is a lot more mind-blowing. All right, I will come to this a little later on. So because atoms, nearly all the atoms around us are empty space, it's technically possible. Hear my words, eh? It's technically possible to walk through a wall. It is technically possible to take your hand and pass it through the table. Is it realistically possible or possible with our current technology? No. Remember, the only thing that stops us from doing many things right now is technological issues. Back then, they didn't have a big microscope. They didn't even have a car back then, probably in the 1850s. And by the 1890s, they had cars. Right? By the 1890s, they had steamboats. They had power plants. All right, so look at the difference of 40 years made. And then look from the 1900s to the 1960s. We went from being able to just be on planet Earth to going in space. All right, now we went from 1960s to 2020, where we can send a helicopter on another planet. Sometime this decade, humans will step on another planet. So the only thing that prevents us is technology. And right now, we don't have the technology yet. We have the maths, we have the science, but we don't have the technology yet to make a person walk through a wall. But it is technically possible because all matter is basically empty space. Let's blow your mind with that for a bit, all right? So there are people who are looking how we do this and whatnot. It's technically possible. As we say, I always say science fiction, imagination breeds science. We need to have imagination in order to come up with new science. You all ever saw the original Star Trek? You all know about Star Trek, right? I hope. All right. This is back then, right? In Star Trek, you all know that they have something called a teleporter where they convert a human into a signal and they can send them through space into another machine or another planet. We've kind of done that already right now, not with human beings, but with really small atoms, and with light, we've actually converted it into an electrical signal, passed it through a wire, and recombined them in another place. We've done it already. Back then, cell phones, they didn't even have the mobile phone. They had cell phones in those TV shows, right? And whatnot. So if you can imagine something, it can happen. The mathematics that was used to send the shuttles and stuff into space was devised in the 1500s, but they didn't have the technology until 1940. All right, so here it is technically possible to walk through a wall, but we don't have the tech as yet. But the maths is there. No, it is not crazy talk. All right. Crazy talk was being able to leave planet Earth. All right. Crazy talk was a cell phone. Crazy talk was being able to see into the human body and see what a baby looks like in the womb. That was crazy talk many, many years ago. Well, not that many. All right. So here from the Geiger-Mason experiment, we went from plum pudding, which of course is very laughable and silly, to knowing that we have a nucleus that has positive charges. They didn't know about it as what the positive charges were yet. Right? We know that we had a nucleus, and very far away, we had our negative charges that balanced out our equation. Right? Meaning if we have we'll have the same amount of negative charges spinning around our atom. So look, in one experiment, we went from what on earth is that, a plum pudding something, to something that actually looked scientific, where we had a ball of positive charge surrounded by rapidly moving negative charges. So we were getting there within one experiment. This is why I tell you, this is the one experiment that changed the atomic physics world. All right, this changed everything. All right, so moving on, we have I will post this up in the Google Classroom so you all can give it a read. Please do. Anytime you all see names here, right? We have Rutherford, we have J.J. Thomson, we have Geiger and Marsden. Read upon these guys, right? They did amazing work in discovering what the atom is made up of. So not too long after the Geiger-Marsden experiment, Ernest Rutherford proposed the existence of the proton. So here, this is where once you have an idea and you start performing experiments to prove your idea, right, you're going to start discovering things. You're not just going to sit down there, fold up your arms, swell up your face and say, you know what, we don't know. No, right? You do experiments and say, you know what we were doing was wrong. Look the right way here. And now you start making more hypotheses, which is a statement to investigate. And we start exploring how we can prove our experiment to be right or if it is wrong. So Ernest Rutherford proposed the existence of the proton, and we know that the proton is a positive charge, right? This is a positively charged particle, right? And from experiments, they had already seen that a particle, your proton, is much heavier than the electron, and it has a +1 charge, right? So by the time the Geiger-Marsden experiment was done, they had discovered the electron in other experiments, other people, of course, all right? They had realized that electrons had a -1 charge, and then that the proton, or whatever was inside of an atom, had a +1 charge. So here they were trying to figure out, so what is this little particle made up of? How many are there? Where is it exactly? Is it sitting by itself? How many does it have? How many can it possibly have? All right, now the proton, of course, did not explain an unaccounted mass found in the atom. This unaccounted mass is your neutron. We're going to go on to neutron discovery the next day. All right, so read it out. So we went from plum pudding to saying this is the 1900s, late 1900s, the 1980s, and the, not 1880s and the 1890s. This is what our atom now look like, which is basically what we have today. All right, so as I said, one experiment changed everything. So you all go ahead, read it up through, read upon all these guys' names you're coming across. Then there's the confirmation of the neutron, James Chadwick, he won a Nobel Prize too. All right, I'm speaking about Nobel Prizes, and some people don't know what that is. Some Nobel Prizes are probably one of the top prizes given out to 5 or 6 fields across the planet. We have non-science field like literature, peace, and then we have science ones, one for medicine, one for chemistry, and one for physics, and one for economics, right? Economics is usually a mathematics prize because all the new mathematics discovered today is used to go into economics. All right, so to win a Nobel Prize is basically the top honor, the top honor that a scientist would love to find your name under. All right, no, it's not winning $1 million. $1 million can go away pretty quickly, depending on where you live. All right, but have your name down forever, to be forever known, all right, is a pretty amazing thing. So here we have the confirmation of the neutron. We're going to do that next day. We're going to go into atomic notation on the next day, and then we're going to look at isotopes. If you can finish more of that the next day, we'll finish that out. Okay, so let me stop the share there. So that is it for today. That's wrapping up for 2 minutes. So I don't know as yet when we're going to have labs. I start labs with my 4-5 on Monday, but you all should be coming up not too far afterwards. I'm pretty sure you all will get scheduled for labs this term, but if not, we're just going to continue working on. So give some reading up on the topic we've done. I will post the quiz for sure this evening on the worksheet I posted. So I gave you the worksheet so you can sit down and start working out the answers and whatnot. So when I post the quiz, right, which will be the answers to the questions in the worksheet, you can just post up your answers. Now, if you did the working properly, your answers will be correct. And I'll post up the solution sometime next week. So you'll see where you went wrong, where we went right, and any stuff like that. So everyone have a good weekend, and I will see you all next week. I will not see you all next week Wednesday because I will be in lab with my upper 6, but I'll see if I can record the video beforehand. All right, so everyone have a great weekend. All right, and be safe, and I will still see you next week, but not next week Wednesday. Bye-bye.
Bye, Miss.
Bye.